In this lecture, we look at the moment of inertia. A form of Newton's second law holds for rotational motion. You may recall from linear motion that Newton's second law had the form of the force is equal to the mass times acceleration, or F equals ma. For rotational motion, the equation looks like this. It's torque is equal to the moment of inertia times the angular acceleration, or tau is equal to I alpha. The moment of inertia I plays the role of the mass for the rotational motion. For a single particle, I is equal to the mass times r squared, where r is the distance from the axis of rotation to the mass. We learned this back in our rotational kinetic energy lecture. For solid objects, they are made up of many particles. Here we have an example of a board that's going to rotate around the axis indicated by the black dot. We show a small piece of mass of the board, labeling it dm. R is the distance from the axis of rotation to that small piece of mass. The moment of inertia for the entire board is the sum of all the moments of inertia from each piece dm as you cover the board. Or in other words, the total moment of inertia for the board is equal to the integral of r squared dm, where the r is, it gives the position of all the different dm's as you go across over the board. Let's look at an example. Here we look at a thin rod that's going to rotate about one end. Its length is L and its mass is capital M. Here's the rod, and here's the rotation. And the moment of inertia for the rod rotating about one end is equal to the integral from 0 to L, so over the whole length of the rod, times r squared dm. This is a one-dimensional problem because it's a thin rod, so we just have to figure out what dm is in terms of the variable r, which goes along the length of the rod. Well, dm is just equal to the mass divided by the total length times dr, a small piece of that distance along the rod. So then we can do an integral from 0 to L of r squared times m over L dr. And we rearrange a little bit, and I is then equal to m over L times the integral from 0 to L of r squared dr. That integral is relatively easy to do, and that just becomes the integral of r squared is just r cubed over 3, so we put that in. Then if we evaluate at the limits of the upper limit of L and the lower limit of 0, we have m over L times the quantity of L cubed over 3 minus 0. Solving that, it's just the mass times the length squared divided by 3. So we can see that changing L changes the moment of inertia dramatically. If you double L, I goes up by a factor of 4. So the next time you go to the circus and you see the clown balancing a long, thin rod on its nose, realize that the clown has it easy. That long, thin rod doesn't want to rotate because there's a very large moment of inertia.